So I often get questions about the hyperbolic cosine and hyperbolic sine function, or cosh and sinh, as most people call them. So I thought I'd say just a couple words about it. So sometimes they're not covered in a standard calculus course. They're supposed to be, but there's not always enough time for everything. So the cosh function is defined as e to the x plus e to the negative x divided by 2, and the sinh function is defined by e to the x minus e to the negative x over 2. So what does that look like? Well, let's just zoom in here and I will draw a little figure. So we'll take our axis, something like that. Okay, so if I look at e to the x, it's going to look something like this. So there's my e to the x, and then e to the negative x is going to look something like that. Okay, so there's e to the negative x. And then cosh, by its definition here, this is just the midpoint between e to the x and e to the minus x, right? When you add two things together and divide by 2, you get the midpoint. So that means if I look at this point here and this point here, cosh should be exactly what's in the midpoint of that line connecting those two. And so the cosh is going to be something that looks like that. Okay, so there's cosh x. And in particular, hopefully you can see from this, or else you can see just by looking back at the definition, that cosh of 0 is equal to 1. Some other things should be evident from this picture, and that is that cosh x is always at least equal to 1. So in particular, it's always strictly positive. And also, cosh is an even function. So cosh of minus x is equal to cosh x. So in other words, it's symmetric. If you were to reflect it across the vertical axis here, you have the same values at either point. Okay, now what about sinh? Let's switch to green. So sinh is the midpoint between e to the x and negative e to the minus x. So negative e to the minus x looks like this one. So here's negative e to the minus x. And so sinh is halfway between that and e to the x that we saw up here. So connecting the midpoints between these curves would get you somewhere right around here. And in particular, you can see the midpoint between these curves at 0 is going to be 0 itself. So this curve is going to pass through 0. And it's going to look like that one, basically. Okay, so there's sinh of x. So we see that sinh of 0 is equal to 0. And we see that sinh x is greater than 0 for x greater than 0 and increasing, and also that sinh x is negative for x negative, and it decreases as you go to negative infinity. And we also see that sinh is odd, meaning that sinh of minus x is equal to minus sinh x. Okay, so there's a bunch of facts about the hyperbolic sine and cosine functions. That's really all you need to know. Those are the essential facts. Key point, cosh of 0 is 1 and sinh of 0 is 0. That's what comes up the most in this particular course. Here's just a couple of other things. So if you look at cosine of x, the power series for it is minus 1 to the n, x to the 2n, all over 2n factorial. And the power series for the hyperbolic cosine just looks like we've erased that alternating part, so there's no negative terms involved in it. And that's why it's called the hyperbolic cosine, because from the power series perspective, it looks just like the cosine function. And then the sine function, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And again, the hyperbolic cosine function looks exactly the same, except that we delete the alternating portion of it. As a consequence of the fact that these the power series work out so well, and from this, before I even get onto that, you can see that the terms in the cosine and cosh, these are all even, and that is why it's an even function. And for sinh and sine, they are all odd terms, and that's why you get an odd function. Okay. Because of these power series definitions, there are identities very much like the usual trig identities for the hyperbolic functions as well. So for instance, you recall that cosine squared plus sine squared gives you 1. Well, cosh squared minus sinh squared equals 1. And similarly, there's other very close analogs of the usual trig identities for the hyperbolic cosine functions as well. Again, we're not really going to need any of that stuff. I'm just sort of throwing it out there for your general knowledge. So when you have something like tangent and it's defined as sine over cosine, then the hyperbolic tangent is just going to be the hyperbolic analog, so sinh over cosh. And the same with hyperbolic secant and tangent, or cotangent and cosecant and all that business, right? That won't really come up for us so much. It's just kind of a convenient shorthand for when you have an expression that has a bunch of these exponentials that look something like this. There's a hyperbolic tangent in terms of the exponential definition. What does that guy look like? Let me draw the axes real quickly here. Boom. Okay, so if we have asymptotes here at -1 and 1, then this hyperbolic tangent looks like something like this. So it looks a lot like the arctangent function, except instead of going from -π/2 to π/2, it goes from -1 to 1. And the convergence is a lot more rapid. So if you were to compare this with the arctangent function, the arctangent function is, so it's π/2, like sort of -1.5, something like that, would go kind of like this, much more slowly. The hyperbolic tangent function is closely related to what's called the sigmoid function, which is 1 over 1 plus e to the minus x. And this one I'm just throwing out there is commonly used in statistics, especially with the advent of machine learning. It's used as the cutoff function for an artificial neuron, because it gives you something that goes from 0 to 1, but smoothly. So this is an infinitely differentiable function, so it goes from 0 quite rapidly up to 1, and then stays constant at 1. Except, I mean, it doesn't quite actually reach there. It's again, this is asymptotic on both sides. It's not quite reaching it. Anyway, that's the hyperbolic sine and cosine function.